Hi everyone. I thought I would take the time to record a small mini lecture looking at some of the qualitative analysis concepts that we looked at in class and some of the ones that we didn't get to before the end of last class because we were all mentally done for the day. So this will hopefully help you to have a tool that you can use when doing your assignment as well as studying for exams. And we will sort of run through some of the main things that you will have to be able to know, and then you can keep watching it over and over again as much as you needed in order to help the concepts gel. So this is the slide that I hadn't actually put the diagram in the slide during the last class. Someone asked me to put it back in, so I thought maybe I would include this slide in the lecture just as a review of quantitative designs. This is mostly a review of class number 2. So this particular is a decision tree. This picture is a decision tree that looks at helping you decide whether or not what kind of study design you happen to be looking at. So first question to ask is, did the researcher assign the exposure? If they did, then you're likely to, an exposure could mean intervention or treatment as well. If they did assign it, then you've got an experimental study. If they did not assign it, then it's naturally occurring, then it is an observational study. So if it happens to be an experimental study, next question you have to ask is, did they randomly assign those participants to different groups? And if they did, then it's a randomized controlled study trial. And if they did not, then you're looking at a non-randomized controlled study, or what we usually call it, we've called a quasi-experimental study. On the observational side of things, you need to ask, is there may be a naturally occurring variable, but is there group comparison going on? And if there is group comparison going on, then you're dealing with some kind of analytical study. And if not, then you're dealing with a descriptive study. If it's an analytical study, it depends on the direction of the study as to what kind of study it might be. So, for example, if the direction of the study is going forward in time, it's probably a cohort study, meaning they're starting with a large group of individuals for which that they possibly know the exposures, but they're watching them over time to see if diseases develop. The second kind being case control. Case control is often retrospective. Retrospective studies mean that you start with individuals that have already developed the disease and compare them to individuals who did not develop the disease, and you look backwards in time, often through their charts, to see if they were exposed to anything. And then lastly, there's cross-sectional studies, and cross-sectional studies look at both the exposure and the outcome or the disease at the exact same time. So that's that diagram, and it's there for you to refer to. Next, we're going to talk a lot about reading statistical information. So statistical information comes in the results section of your study. And the methods section will outline where those tests were used and specifically what tests were used. Okay. And you should know the different abbreviations of the various tests. So a t-test is a little t. Okay. An ANOVA is a f. A chi-square is an x, or x squared. Okay, so you'll just need to know those little abbreviations for those different tests. That way, when you read them in the articles, it's easier to pick them out. Your reading research book will show all this for you too as well. Often it's best to start by skipping the results section. So read the discussion first. I know I've talked about that before in class. It is a really good strategy. It helps you give sort of a more summarized version of what the main findings were. Before you go back and look at the details in terms of the statistics in the different tables. Okay. Then you want to also look, because it's not always in a table, but you want to look in the results section for a very short description of the demographics of the sample. Or, as I said, it could also be in a table. And that will speak to the generalizability of the study findings, because what you want to assess in looking at the demographics is if you sort of can get a sense of if that population is similar to what the total population for that kind of participant might be. All right, statistical tables. So unfortunately, there's no one standard presentation for the way tables are laid out in studies. And so we're going to take a look at several tables, and sort of try and give you some tips as to how to read them. Okay. There's usually often also to accompany the table a description in the body of the article, in the spot where it says, see table 1 or see table 2. That's the part you want to read that might enlighten you to how to read the table. So sometimes if I'm skimming an article and I just look at the actual table itself and I don't quite sure what the table's trying to tell me, I will go back to the text and I'll look for the spot where they say see table 4 or whatever table it is I'm trying to read, and I'll read the little blurb there, and that usually will often begin to enlighten me as to what it's about. Okay. Pay attention to all the table titles, headings, footnotes. Okay, they give you a lot of really good information about the table, and we'll show you how that works and we show you some examples. So things that you want to look for in every table, and what I'm going to talk about in my discussion today, are you want to look for any evidence of the name of statistical test that they did or the abbreviation of that particular test. This is why you need to know the abbreviations, because sometimes they don't name the test in the table. They just give the little symbol that the test stands for. Okay. You want to look for the value of the calculated test statistic. So that's not always given in every table, and I'm hoping that we've got examples that have it both ways. But there's usually a column. You don't usually have to do too much with the column of the calculated test statistic. You don't have to evaluate it in any way, because we use the p-value instead to assess whether or not that test statistic was important. Okay. So the next thing is to look for that level of significance, the p-value that was calculated from the test statistic. So you look at that, and it's either usually in a column actually spelled out for you, or sometimes they use asterisks in the table, and the asterisks will represent varying levels of statistical significance, and we'll show you an example of that as we go through some tables. Next, you want to look for the number of groups being compared in the table. So the number of groups being compared in the table can be a hint to what the statistical test was that was done in that table. Because if you know the level of measurement, which is the next thing to look for, if you know the level of measurement of the data in the table, via whether it's giving you percentages or mean, medians, and modes, okay, then you'll be able to, and you know how many groups are being compared, you'll be able to give your best guess as to what statistical test was being done if they haven't named it explicitly in the table itself, but they should be naming it explicitly. So here's an example of a table. We can take a really quick glance at this table, and we can look at what kind of information it's giving us. So we see we've got a section of the table that's describing the control group. These are pre-intervention and post-intervention measurements of body size and self-reported behaviors. And it's got a control group, and it's got a smartphone plus health coach group, which we can assume is the experimental group. Okay, so we've got different other columns below that. So we have under the control group, we've got a pre column, a post column, and then we have a column that's labeled P with a little A. That little A in the legend tells us that it's a comparison of post versus pre in the control group. And so it's telling you specifically what it's about. Okay. And then on the other side, we have pre and we have post, and we have two columns of P's. So that the first column of the P is associated with the p-value associated with the experimental group, pre and post test. And the next next P column, what's got the little hyper C on there, is looking at the change between groups together. Okay. So this is just one example of the way tables can be laid out. This is actually not a typical example of the way I've seen tables laid out, but it's still one that can be effective. Okay. So the first thing that I would do when I'm assessing statistical significance is I would look down these columns that are P, and I would look for, if you remember that the threshold for statistical significance is P is less than 0.05. Okay. So what I would do is I would scan for any numbers that are P less than 0.05. So in the control group P column, we have 0.76, 0.81, 0.96. They're all greater than 0.05. 0.27 is still greater than 0.05. 0.25 is still greater. and we have 0.09. So we don't have anything that was statistically significant. So this is the control group, and it showed nothing that changed statistically significantly over time, from pre to post intervention. Assuming again, of course, that the control group did not get the intervention, this would be the expected finding, right? That nothing changes in the control group over time because they have not been intervened with. Okay. The numbers in brackets, they're not telling us exactly what they are, but I would assume they're either confidence intervals or they're the plus minus of the standard deviation. It's really sort of unfortunate that they don't tell us exactly what they're doing, but it's likely probably the plus minus of the standard deviation of around the mean, and you don't have to worry about that for this particular talk. Okay. So the next, under the P column that goes along with the experimental group, though, as you can see, we're looking for P's less than 0.05 in the first column, the P with the little b at the top. You have one that's, the first one's less than 0.01, the second one's less than 0.01, the third one's less than 0.01, 0.032, all still less than 0.05. We have one here that's 0.151, so that one's greater than 0.05, and another one here that's less than 0.01. So you can see we can read this table without even knowing what kind of variables they're looking at here, like the column over the side. They're looking at some factors of body weight and some factors of self-reported behaviors, are what they were looking to see change over time. So this again would be the expected findings for an experimental group. You could, that in a group that you would expect to change over time because they received an experimental intervention that should cause them to change. Okay, so you'll note that they're all statistically significant with the exception of one. You rarely get perfect results as expected in studies. The last column compares the change, the difference between the control group and the experimental group. So this is like that post-test 2 time period that looks at the difference between the control group and the experimental group. And again, we would expect that there to be differences between them because the control group did not change and the experimental group did change. Okay, so we have P equals 0.026, 0.024, less than 0.01. These ones are all less than 0.05. So there was a statistically significant change or difference between the experimental and control group on these first 3 variables. The last 3 are all greater than 0.05, so they were not statistically significantly different. So that's just a little bit about how to read that kind of table. Okay, so this is a table that looks at a randomized controlled trial, I would assume. This is correlational tables. Now, there are often 2 very common presentations of correlational matrices. We call them correlational matrices. The first one, as you'll see, they list all the variables down the side, and then all they do is list numbers across the top. So in correlation, if you remember, what we're doing is we're comparing each variable to each other, okay? And we're looking to see what the relationship is between these individual variables. And the 1, 2, 3, 4, 5 down here on the side on the top table has the same meaning. They're the same variables across the top. So but they're just putting the number 1, 2, 3, 4, 5. Okay. So the way we read the tables, we look for intersecting pieces. So if we want to know the relationship between psychological distress, which is number 5, okay, and number 4, conduct problems, okay, we would look for the spot where number 5 and number 4 intersect. So I would go across the bottom line here, number 5, and I would go up to the column that's labeled number 4 at the top, and we find out that the R value or is 0.36. Okay, you'll note that 0.36 has a little asterisk beside it, and what that little asterisk is telling us is that that's a statistically significant correlation. That's P less than 0.05. Okay, so that's a correlational matrix. That's one style of it. The other style is where they just actually list the names of the variables both along the column and along the top row to tell you to help you get where to intersect. Okay, so if we want to know the relationship between mood disturbance, which is the second one down, okay, and trait anxiety, which is the 4th one down, we're going to go to the one that's got the higher number, trait anxiety, and we're going to go to where mood disturbance is in the table. There it is. It looks very tiny, 0.65. It's got 2 asterisks beside it, which means that it's statistically significant. Okay. and the correlation is significant at the 0.01 level with 2 asterisks. This is another common thing they do in tables, is that they don't just tell you which numbers, which R values actually meet that P equals 0.05 threshold. Okay, they'll break it down into segments, right? So they'll tell you which ones are meet 0.05, which ones are actually even more significant of that at 0.01, and sometimes there's a 3 asterisk, and that typically stands for that the statistical significance is less than 0.001, so it's even smaller yet. Okay. Now remember what we've talked about related to correlations, that there are strong correlations and there are weak correlations, and 0 is considered the point at which there's no correlation, and 1 is a perfect positive correlation. So the other thing you'll notice about these two tables is that the bottom one actually puts the 1s in, and that represents where the variable is correlating with itself, which of course should be a perfect positive correlation. So there's the 1s there. This one here doesn't even acknowledge that one at the top. It doesn't acknowledge it. It just puts little dashes in the spot where the 1 would go, because it's kind of useless information. It's useless to know what the correlation is between a variable and itself, because we're not usually interested in the variable's relationship with itself. We're interested in its relationship with other variables in the study. Okay. So remember that correlations, a strong correlation, we generally say is anything greater than 0.5. And 0.7 is what's used when we want to look at correlations that are trying to represent reliability or validity coefficients. So I don't think we have any that are greater than 0.7 in this particular table, but we do have several that are greater than 0.5. This one here, that's mood disturbance and uncertainty, which is 0.57. And we have the one that we looked at, which was 0.65, which was mood disturbance and trait anxiety. And also trait anxiety and state anxiety, 0.53. And then we have others that are lesser. And you'll note that like there's some, they're statistically significant at 0.3 approximately in this particular table. And that varies from table to table. You'll see with really large sample size studies, you'll get statistical significance even when the relationship or the R value is like 0.1, which is not a strong correlation at all. So you have to question its real world applicability, even if it's statistically significant. Okay. You'll note also some numbers have negative signs in front of them. Those would be negative correlations or inverse correlations, meaning that as one variable that the value goes up, the other variable, the value is going down. But it doesn't look like any of the negative correlations were statistically significant in this bottom table. In the top table, we've got a couple of negative ones. Psychological distress was negatively related to, I guess, 2, which is parental control, 3, which is parental warmth. Okay, so those ones are negatively related, and conduct problems looks like it's negatively related to some things as well too. Okay, all right. This is a table that looks at chi-square examples. So what they've done here is they've got a relationship, association between respondent characteristics and perceptions of coronavirus 2019. So this is looking at people's various personal characteristics and what the statistically significant relationships are. So we can look at a number of different things. They've got like 6 or 7, 8, maybe 8 different columns in this particular table. And they've got several different variables that they're looking at what's related to personality traits. Okay. So they're looking at the top, the characteristics of the participants are looking at sex, they're looking at age, and they're looking at profession. Okay. And so we'll take a look at the one that's about sex. And we'll look at the first one. COVID-19 symptoms appear in 2 to 14 days. This is a question that was asked in a survey, and they were to state that they were to say yes or no to this question. Okay, so the way a correlational matrix, the way a chi-square table is set up is that you've got 2 variables. You've got 2 groups being compared, males versus females, but you've also got 2 response options, yes versus no. That they are looking at. So under the yes column, under males, 198 males in the study said yes to that. 183 males said no. Okay, versus 183 females said yes. 36 males said no, and 36 females said yes. So that looks like fairly equivalent between genders. So if I was to look at, to guess what the statistical significance might be, I would guess that that's non-significant because the males and the females are too similar to each other in their responses. And in fact, when we go to the column that says p-value right beside it, it's 0.75. Okay, is the p-value. So that's highly non-significant at all. Do we have any that are statistically significant in this table that we can take a look at? So we can look at p-value 0.75, 0.19, 0.94, 0.67. So none of these ones in the first column are statistically significant. In the second column, we've got a 0.001 here on the top. So we can take a look at that one. 0.78, 0.07, which is close to significance, but isn't. Nothing else that's significant. So we have two that on the top row, a 0.011, which is also statistically significant here under profession. So let's take a look at the the first question, COVID-19 symptoms appear in 2 to 14 days. And we'll look at the difference in age group responses. So they've got it actually in 3 age group responses. So that's going to be probably a Friedman's test rather than a chi-square, but it's the Friedman's and chi-square are the same test. It's just that one compares 2 groups like male, female, and the other compares 3 or more groups. Like in this case, age is lumped into 3 different groups: less than 25, 25 to 44, and 45 to 65. Okay. And so let's take a look at our different variables. We've got less than 25, 130 said yes. 25 to 44, 207 said yes. And in 45 to 65, 39 said yes. Under the no side, age 25, 15 of them said no. 25 to 44, 26 said no. And 36 of the 45 to 65-year-olds. So we what you want to do is you want to look at also at the percentages, and what you can see is that you got very similar responses happening between the less than 25s and the 25 to 44s. About 89% said yes in those age groups, but only 52% in the older age group said yes to this particular question. And so it seems that there's a difference between this 45 to 65-year-old age group, that the older people seem to be less knowledgeable about facts about COVID-19 than the younger age groups. And it was statistically significant. Okay, so that's a chi-square group. And then one of the ways that I know that it's a chi-square table, even though it does not tell me that it's chi-square, is there anywhere where it's got an x squared? Not that I can see. But I know it's a chi-square table, probably because the text of the article told me so, but also because we're comparing 2 groups and we're looking at nominal or ordinal level of responses, because it tells me in the column here that these numbers in the main part of the table are n%. Okay, that they're giving you the sample size, and the part in brackets is a percentage. And whenever a nominal and ordinal data are represented by proportions like that with percentages, whereas interval and ratio data are represented by mean, medians, and modes. And we don't see any mean, medians, and modes in this table at all. So that's why I know it's a chi-square type of calculation. Here's an example of an ANOVA, and actually this is a table out of one of my own studies. And this is an ANOVA table that compares 3 different groups, and it's one that I think that I talked about in class, where to look for that sort of known groups kind of validity, to find out whether or not those who like writing, feel somewhere in between, or dislike writing, have different levels of self-efficacy. And it turned out to be very, very strong. Okay, so this is yet another different type of representation of a table, because you'll see that I represented the statistically significant results in a very simplistic way, because all of these, this is your test statistic column. Okay, every single one of those F's was statistically significant. So I just wrote a little asterisk here beside the F and put into the legend all F values p less than 0.001. They were all highly significant. Okay, and all groups were different from one another. So I looked I looked at the total scale, I also looked at the different subscales, the writing essentials subscale, the relational reflective subscale, and the creative identity subscale. And every single subscale was different, with those individuals who reported liking writing consistently having high writing self-efficacy, and those who said that they dislike writing consistently having the lowest writing self-efficacies. So that's a fairly easy table. And the reason why this is ANOVA, other than the fact that I've told you in the legend, because I've been teaching research for a long time, and I know that it's really makes things a lot easier for novice readers of research when you name the statistical test in the heading of the table. So I tell you what kind of test it is. It's a one-way ANOVA. But I would also know whether I'd written that or not, because it's 3 groups. Okay. And the data in the table is represented as means and standard deviations. And I tell you in the legend, mean, standard deviation, and one-way ANOVA results for self-reported rating attitude and SOSIS, which is the name of the questionnaire. Okay. So that is an ANOVA table, 3 groups, interval and ratio level data that I know it's interval and ratio level data because it's mean standard deviations that are reported in the table. All right, confidence intervals. Now, confidence intervals are important for your assignment. And confidence intervals are a range of values that are likely to contain the true population value with any sort of degree of certainty. And that degree of certainty is often set at 95%. And yes, that 95% is the opposite of that p equals 0.05 number that we use to identify statistical significance threshold. So it's just, 100 minus 0.5 is 95%. Okay, or 0.1 minus 0.05 is 0.95, which is the same as 95%. Okay, this means that you can be certain within 95% that your true population values will fall somewhere in the range that they give you for the confidence intervals. And we'll look at a table example of this. Okay, so confidence intervals can be placed around all kinds of values, right? There isn't any one specific kind of value that they put it around. So difference in means is really, really common. They can put them around effect sizes. They can put them around rates. In fact, the example that we're going to see in this particular set of slides looks at it around rates. Around odds ratios, you can put them around correlation coefficients. I would say the most common thing that you see them put around is difference in means, as well as odds ratios. Odds ratios are a calculation that's often used in case control and cohort studies. We haven't used an example like that, and that's not the example that's in your assignment either. So if the confidence interval is equal to or crosses over 0, then the calculation is non-significant. This is why this is important to know, because a more recent trend in reporting of results is sometimes they won't tell you the p-value, but they'll give you the confidence intervals. And so if you see a confidence interval cross over 0 in some way, and I'll show you what that means on the next slide, then you know that it's a non-significant relationship between those groups, or whatever it is they have, or non-significant, R value, correlation coefficient. It really depends on what the number is that they've got the confidence interval around. Okay. Narrow confidence intervals are better than wide confidence intervals, because obviously if there's a much tighter range of values that your true population mean would fall into, then the likelihood that your number that you got in the study is correct is even more likely to be correct. So here's an example. In fact, this is a diagram from this website that you see listed here, and this shows you again like your normal curve, as they call it, with lines at the 95 confidence interval part. This means that this is the range that all your population values could fall in, is between these two blue lines, and that's your 95% confidence interval. Anybody who has values outside of those are considered outlier values, those that are extremely high or extremely low. Okay, so to give you an example, in this case, in the picture diagram example, they say the mean is 0.427, and then they tell you what the lower limit is, 2.92. And the higher limit is 5.62. Sorry, it's really small on my screen. Those lines are at the actual upper and lower limits of the confidence intervals. So if the confidence limits are minus 0.1 to 6 with a p-value of 0.07, with a difference in means that's at 5, okay, you'll note that the confidence interval crosses over 0 because one side is a negative number and the other side is a positive number. So the lower limit is minus 0.1 and the upper limit is 6. So it crosses over 0. And in fact, we've got a p-value that's associated with it that's not quite significant. It's 0.07, which is bigger than 0.05. Okay. If your difference in means is minus 11, for example, confidence limits could be, say, minus 13 to minus 8. That does not cross over 0. It stays in the negative range, just like the difference in means. In fact, because it doesn't cross over 0, we know it's statistically significant. And I've given you these are all fabricated results, a p-value that's equal to 0.001. Okay. So you must know, again, in a way to assess these confidence intervals to decide whether they're narrow or whether they're wide. It really depends on knowing the possible range of confidence limits that could be. So if they're giving you a difference in means, for example, okay, so you have to know then what's the possible range of the tool that they've used that gave you the mean to begin with. So if you've got a scale that they're giving you a difference in means on, and the range of that particular scale can be between 0 and 16, okay, then you know that your confidence intervals are only going to fall between 0 and 16, the possible range in the confidence intervals. And so the tighter it is, if your confidence interval falls between 1 and 15, that's a really wide confidence interval. Whereas if it falls between 12 and 13, you know you've got a really narrow confidence interval. Okay, I hope that makes sense. It's a tricky concept, and you're welcome to ask me about it in class next week. So here's a confidence interval example. This looks at a study about rates of nursing errors and handoff-related errors in a medical unit following implementation of a standardized nursing handoff form. So they had an intervention study where they created a standardized nursing handoff form that nurses were to use during shift report. Basically, that's what handoff is referring to, is shift report. This is the abstract for the article. It's a very, very short abstract. So this a standardized nursing handoff form was designed and implemented to improve handoff process, and rates of nursing errors were measured to determine the effectiveness of the intervention. So this study was a prospective intervention study using a one-group pre-test, post-test, quasi-experimental design conducted at an inpatient medical unit, and the rates of nursing errors decreased from 9.2 with a 95% confidence interval of 8 to 10.3 to 5.7 with a 95 confidence interval of 5.1 to 6.9 per 100 admissions. So in this case, they're putting their confidence limits or confidence intervals around a rate of occurrence of an error in this case. Okay, so this is comparing the pre and post intervention periods, and these were statistically significant. So we'll look at what I've done is I've put the table from this study, okay, into these lecture slides. This is the table from the same study, okay, and you'll see in this table, just to examine it, that the table is telling us about the total number of errors. That's the number that's not in brackets. The number in brackets is referring to the rate per 100 admissions. And the number in the square brackets is the confidence interval, the 95% confidence interval limit. And you'll see how that's represented in actual numbers in the actual table itself. So there are two groups. In this case, 2 time points before intervention and after intervention. Okay. And it gives you the x squared. So it tells you that this is a chi-square of some sort. Two time points is a chi-square. Okay. And it's got and it gives you a p column. Sometimes usually it's little p, but this looks more like a capital P, but that's what it is. And usually, again, the first things I do when I see tables like this is I'll go down, I'll take that p column, I'll take a highlighter, and I'll highlight everything that's less than 0.05, just for my own, eyeballs to be drawn to it. Okay, so less than 0.001, less than 0.001, 0.002, 0.03, less than 0.001. We have lots of statistical significance. 0.04 is statistically significant. 0.16 is not, 0.73 is not, 0.10 is not, 0.80 is not, 0.91 is not, and 0.52. So the numbers they gave us in the actual abstract refer to this total nursing errors line. So they told us that before the intervention that there was 180 handover errors made. After the intervention, there were only 112. Not only, I would say 112 is still a pretty significant number of errors. And then, so the 180 refers to the total number of errors itself. Okay. The part in brackets refers to the rate per 100 admissions. So 180 errors translated to 9.2 errors per every 100 admissions. On the other side, 112 errors translated into 5.7 errors per 100 admissions. Okay, and then the confidence limits, 8 to 10.3, which is what we saw in the abstract, and 5.1 to 6.9. Now, given, again, like I said, you need to know sort of what's the range of possible numbers that the confidence limits could fall into. In this case, it's almost infinite. It can go as low as 0, obviously, because you can't have less than 0 errors. You can have only 0 errors, or you can have a number of errors. And then the number could go as high, potentially, as we want to. In this case, it could go as high as 180, or on the 112 side, as high as 112. Okay, but this, or sorry, in terms of the rate per 100 admissions. So it would actually be 0 to 100. So 0 to 100 error is the possible number of errors that you could see in this particular rate. And the confidence limits is around the rate, not the total number of errors itself. So 8 to 10.3 is actually really, really narrow. 5.1 to 6.9 is really narrow to be around 5.7. So that is a really, really tight. This means these results are fairly confident that this is a true statistical significance in change in number of errors before intervention to after intervention. Okay, so that's really strong. And what they've done here in this table, and you can kind of pause the video and you can stop and study them all, but you can look at the different types of errors that they were looking at specifically. So delayed admission of medications, pressure ulcer, inappropriate care of line, so they're looking at a number of falls. They're looking at a number of different things that went on. Okay, so you can study all of those and see the difference between them. All right, second to last slide, effect sizes. Effect sizes are also something that are part of your assignment that you need to look at. So an effect size is basically a quantitative measure of the magnitude of the success of the intervention. So it's calculated whenever you're comparing two groups, or it can be calculated whenever you're comparing two groups. But one of the things that you'll find is, and in fact, I didn't spend a ton of time looking, but I did actually not find an article that used an effect size that I could give it as an example. It's so rarely talked about. It's not to say you couldn't calculate it yourself, but we under no circumstances expect you to calculate it yourself. Okay, so the calculation for effect size, the main one is known as Cohen's d, and this is diagram, this formula over here on the right hand side is the Cohen's d calculation. And what they do to calculate effect size is they take the mean of the experimental group minus the mean of the control group, okay, and they divide it by the standard deviation for the whole population. So that would be the experimental group and the control group, their standard deviation added together, okay? So that's how they calculate effect size. And the numbers that come out are in the table above it. So it's considered a small effect size if that calculation is around 0.2. Okay, it's a medium effect size if the calculation is around 0.5. Okay, and it's a large effect size if it's 0.8 or greater. Okay, and what it basically means is that obviously the larger your effect size, the greater the impact that the intervention had on the population. Okay, so that's kind of a way of assessing, I guess, clinical or real life practicability of using this particular intervention. It's just a way of calculating that. And obviously, the larger the effect size, the more effect that you're going to actually see something visible in the real world when you actually implement that intervention yourself. Okay. But Cohen's d is not the only type of effect size that they refer to. There are other kinds, and I briefly alluded to this one in class the other day. But correlation is thought to have a low effect size, has effect sizes as well. And Cohen, the same guy who invented the Cohen's d, he's sort of stated blankly that effect sizes of around 0.1 are considered low effect sizes. So correlations around 0.1, medium around 0.3, and large if 0.5 or greater. Okay. There's a third kind of effect size called partial eta squared, and you see this on more complex statistical calculations, and we're not going to look at those today, but I just want you to know, if you ever see reference to partial eta squared, they're talking about effect sizes, and the numbers are different, 0.01, 0.6, and 0.14. Okay. So the last slide is just a review and a summary of all the other thresholds that we've talked about. So confidence limit intervals are one type of threshold. Your effect sizes are another kind of threshold. But we've talked about some thresholds already, in particular reliability and validity thresholds, which are R equals 0.7, or Cronbach's alpha, which is also equal to 0.7. And anything we consider that threshold to be anything greater than 0.7 is considered to be either reliable or valid, depending on what calculation is being done. And then, of course, there's a threshold for statistical significance, where p is equal to 0.05, or we also call it alpha, but not to be confused with Cronbach's alpha, just plain old alpha, mathematical alpha. Alpha equals 0.05. You'll see it referred to in both ways in the study. In the study. So that's the end of what I wanted to talk about on these particular slides. By all means, you can watch this and you can sort of use it as and ask questions, next class about this particular type of content, because it is very complex content. So it's good to have something in what I say to go back to over and over again if you feel the need to do that.